Hi and welcome to this Leaving Cert Higher Level Maths revision video. In this video we're going to look at the 5th year functions exam questions. Question 1 is a translation with completing the square and it's worth 25 marks. The diagram shows the graph of the function f of x is x squared plus 2x minus 3. G of x is the image of f of x by the translation 0, 0 to 2, 2. Part I. Draw a sketch of the curve y equals g of x on the same diagram. Okay, so when we talk about the translations, there's a few different ways that they can present it. This has presented it with the actual coordinates. So it has told us that every point, if it starts, for example, at 0, 0, will end up at 2, 2. So there is the translation. There is the movement. So what we're going to do is we're going to take some key points on the graph. So I'm going to take the root. I'm going to take the minimum point. I'm going to take the y-intercept. I'm going to take the other root. And you can take more, but that should be sufficient. And then I'm going to translate those, move them, the same way that we've been shown, as in from 0, 0 to 2, 2. That movement is 2 units to the right, 2 units up. So my point, my root at -3, it's going to move right 2, up 2, and it will end here. My minimum point, which is -1, -4, it's going to go right 2, up 2. So here is my new minimum point. My y-intercept was at 0, -3, so it's going to move 2 to the right and 2 up. It now is here. I then have the second root was at 1, so I move 2 to the right and 2 up. So now I have my quadratic that has been translated from my original. Now, so if we were to connect these, this is not great. So there's my minimum point and it comes up like this. Now the computer is not great to do drawing on, but you get a sense, the idea. We want to keep this nice and curved, and this is g of x. So we can see that every point moves the same way, and that is up 2 units to the right 2 units. So using those points to translate, this gives us our g of x. So I've just tidied that up a little bit to make it easier to use for the next part. So part 2 says express g of x in the form a plus x squared plus b, where a and b are constants. So they want us to use completing the square. Now, I'm going to show you two methods for this. I think the first method is probably the one that most students would try first. It's probably the most obvious method, but it's definitely more challenging than the second method. Let's look at using the translation to create g of x. Now, the translation is, again, I'm going to show it here using the point that they gave us, 0, 0, and 2, 2. It moves up 2 and to the right 2. When it moves up, this is translating in the y direction, up and down, and it's adding 2 to the y value. When we move to the right, and this is where it gets tricky, the x always acts opposite or backwards to what we'd expect. So here, this translation is actually x minus 2. So taking 2 from the x value shifts this to the right. So using that fact, we will take our f of x and simply add 2 to the y. Remember, f of x is another way to say y, so I'm just adding 2 to the whole thing, and I'm taking 2 from the x value. So you can see here that we can write g of x as f of x minus 2, so taking 2 from that x, plus 2, adding 2 to the y. Doing that is a substitution. So remember, we have f of x. So our f of x that we've been given up here, f of x equals x squared plus 2x minus 3. That is the rule of the function. It's telling us when we get our x, we put it in here. So we square it, then add 2 times that x, then take away 3. Now we're working with f of x minus 2. So everywhere there was an x in the original, we're going to work with x minus 2. So that works out as x minus 2. So I'm going to highlight this so you can keep track of it. X minus 2 squared plus 2 times x minus 2 minus 3. That's the original function f, subbing in x minus 2 instead of x. And then we have a plus 2 there on the end. Tidying that up, so we're going to expand our square brackets. We're going to expand that 2 times x minus 2. Squaring the bracket, we square the first, x squared, twice the first by the second, minus 4x. Square the last, plus 4. Then we get plus 2x, minus 4, minus 3, plus 2. Simplifying this gets us back to what would be a normal looking quadratic trinomial for g of x. Now, we're not finished because g of x has to be expressed in the form that was given in the question. This is completing the square form. So now that we've got g of x, we now have to work and create or work towards making it look like this. There's no coefficient, so that makes it a little bit easier. So what we're going to do is we're going to look at the first 2 terms, so the x squared and the x terms, and we're going to create a square bracket based off those. So that is square root the first, so that becomes x, and then you have the coefficient of the middle term here. So ignore the x because that x is already taken into account here, and then you have here what's left. So divide by 2 and we get minus 1 squared. Now the thing about this is we've taken 2 terms and we've created a square bracket, but a square bracket actually has 3 terms when we expand it. So let's expand it. So that actually makes x squared minus 2x plus 1. So there's an extra 1 included in that square bracket that we didn't actually want. So we can take that away and we still have the minus 1. Or when it's straightforward like this, you can think, well, I currently have a plus 1. I want it to be a minus 1. So how do I fix that? And the answer is take away 2. So my final answer for g of x in that form is x minus 1 squared minus 2, where a and b, remember, were constants. So now let's look at a second method. Now this is going straight to the formula of completing the square. The completing the square formula, I suppose it's important to understand why we do it. Why do we bother putting it in that form? And one of the key ideas or key uses for it is to understand the minimum or maximum point of a curve. So because we have a graph, this is very, very useful. This idea of the form, let me highlight this. This form gives us our minimum or maximum value. We are dealing with a positive quadratic, so we are definitely dealing with a minimum point. So when we talk about it in this form, now I've written it in kind of what we would use with the coefficient and with P's and Q's. But basically, when it's written in that form, we have a minimum point, and the minimum point is given as PQ. So here, where did I get my 1, 2 from? It's the minimum point of my new function. So here, my new function, my g of x, my translated, this is 1 minus 2. So let's look at how we would use that. The p value goes in here. There is a change of sign, that's why there's a minus. Then the minus 2 is the q bit, it goes in there. So I can go straight to subbing in. There is no a because we can see from what I've highlighted in orange above, there is no coefficient. So actually we can write g of x straight down as x minus, let me highlight to follow through, x minus 1. So that's the x coordinate of the minimum point. And then minus 2, that's the y coordinate of the minimum point. So there's my minus 2. And actually that's it. So if you can remember, and like I said, this is probably the less obvious for students, because we don't see it that often. I know we use completing the square to get a minimum point, but remember it works the other way. If you have the minimum point, you can very, very quickly and easily create your function in this form. It then asks us to hence or otherwise solve g of x equals 0. If you worked the first method, you have your quadratic trinomial. You can work through with factorization or minus b. You'll have to look at it. But what they really want us to do, that hence, is using the form we have. So using this form, solve it. So let's work through how we can use this completing the square form to very quickly and easily get the roots. Because remember, that's what solving is. So I'm going to let this g of x equal 0. Then I'm going to add 2 to both sides, which gives me x minus 1 squared equals 2. I then want to get rid of the square root. And now this is the tricky piece you need to remember. We are so used to undoing a square with the square root. I think Pythagoras from the time you were probably in second year. But we often forget to talk about the fact that when you put in a square root, you need to take account that there is both a positive answer and a negative answer. I think a lot of the time this gets lost because Pythagoras, where we see this the most, is dealing with length. So we only have to worry about that positive square root. But really, when we put in a square root, we must take account for there is 2 answers. Often I would direct students to use difference of 2 squares rather than square roots in a lot of cases to I suppose, stop this error. But here we have no choice. We need to square root, but when I place that square root, I take account that it could be positive, it could be negative. So this is what it ends up looking like. X minus 1 is equal to plus or minus square root of 2. If you think about what we're doing, the fact we're solving, we're getting our roots. One method to do this is minus b, and think of your formula for minus b. It is minus b plus or minus square root. So it has that plus or minus. This is a quadratic. We're looking for 2 answers. Finally, we're going to add 1 to both sides. When I do this, I don't put it at the end. I put it at the front. And that way it looks a little bit more like our answer when we do or when we use the quadratic formula or the minus b formula. So that's our answers. There is x equals 1 plus root 2 and x equals 1 minus root 2. Question 2 was an exponential function, but also linked to injective, surjective, bijective, and it is 10 marks. The exponential function f is defined as f of x equals e to the power of x plus 2. The diagram shows the part of the graph where f intersects the y-axis at 0, c. Determine the value of c and the range of f. Okay, so I know that our function here looks a little bit more, I suppose, complex than we would usually see. I would generally tell students to write this in an easier form to work with, so something like this. But what's important here is this part here is actually telling us information. And the first bit that they tell us, this or is our domain. So that is our inputs. That's what we're putting into the function. And then the second part is the codomain. Now that's what we can get out, not what we will get out, because the codomain is the possible y values, while the range is the actual y values. So when we see our function given in this kind of format, what it's telling us is very efficiently what is the domain and what is the codomain. So we can use all the x values and we can use all the y values. So in simple terms, the function is just f of x equals e to the power of x plus 2, but this idea of domain and codomain, it will become important in the second part of the question. So determine a value for c and find the range of f. So there's 2 parts. The value of c, if we look on the graph, c is actually the y-intercept. Now, in polynomials, which we probably deal with more than anything else, that c is the constant. So if it's a linear, if it's quadratic, if it's cubic, if it's degree 10, it's always going to be the constant will give us the y-intercept. Because we're dealing with an exponential function, it's not as straightforward as that. You might have learned the rule of what that will give us. However, it's easier to work through and to think of the y-intercept is where x equals 0. So let's take our function. I've written this with y rather than f of x to help us. We take the point which is 0c. It's the y-intercept, so the x is 0, and we basically sub in. So we want to find c, so the y value, when x is 0. So that becomes c equals e to the power of 0 plus 2. So we're subbing in for x and we're subbing in for y. That's now created a little equation. C equals e to the power 0 plus 2. E to the power 0, you can put it into your calculator, but by the rules of indices, anything to the power of 0 is 1. Remember, power 0 really is something that is being divided by itself. So that gives us c is equal to 1 plus 2, which gives us a final answer of 3. So c is 3. It then asks us to find the range of f. Now the range are the actual y values. So what y values do we use? Now this is a little bit trickier. So e is a positive number. I'm going to break this down. Now again, as you're working with exponentials, you'll start to remember things, or maybe you already do, you remember the rules or the key ideas about it. What I find is students don't for exponentials. They're great with polynomials, but exponentials, we don't tend to use them enough for them to become embedded properly. So look, let's work through this in a more logical way. So e is a positive number. Remember e, Euler's number, it's 2.71. It is a constant. It's like pi. It's not a letter that demonstrates a varying number. It's not a variable, so it's a constant. So remember that. So e is a positive number. Therefore, e to the power of x is greater than 0. So let's think about that. If I take a positive number and I put it to a power, it has to be greater than 0, because there's no way that I can multiply a positive number by itself any number of times and magically make it negative. There's no way. It's not possible. So if I start with a positive base, that big number, and I put it to a power, it doesn't matter what power I put it to, it's going to stay positive. And if you kind of think, well, what about a negative power? Well, think about what negative powers actually mean. Negative powers actually mean they'll make a fraction. And fractions are still greater than 0. They're smaller than 1, but they're greater than 0. So I know that if I take a positive number and put it to any power, and that x can be any number, it will be greater than 0. So then if I can figure that piece out, well, let's look at our actual function. Our function is e to the power of x plus 2. So therefore, taking this, I can add 2 to both sides, and I'd say, well, actually, e to the power of x plus 2 must be greater than 2. Okay, so therefore, I've just worked out that y is greater than 2, so that is the range of values. So my y is greater than 2. That's absolutely fine to write it like that. That is the range. Another way you can write the range is using our brackets. We use round brackets to show that a number is not included. So here, because it's greater than 2, 2 is not included. So we have 2, infinity. Infinity always has a round bracket. Remember, infinity, it's not a number, it's a concept. So these are two different ways that you can write the range of f. So just remember, and I'll just go back up to this line here, e to the power of x is greater than 0. It can't be 0 because there's no way we can multiply it or divide. I think those go hand in hand because some of our powers really do mean divide or multiplying by the reciprocal. So if I think of multiplication and division, like unless I'm multiplying or dividing by 0, which e is not, there's no way it could be 0. It's going to have to be some number bigger than 0. And that's a key idea, and that can be very helpful, and that helps us to get the range of f. So part B, state whether or not f is bijective, give reason for your answer. Okay, so the three things we're going to check: injective, surjective, and if it is both injective and surjective, it is bijective. Bijective 2, and the two things that we want is injective and surjective. So first thing I'm going to do is check to see is it injective. Do this, I'm going to use the horizontal line test. So the horizontal line test for injective basically says if I can draw a horizontal line anywhere and it touches the graph at most once. Okay, that's important because it's okay if it doesn't hit the graph at all, it just can't hit it more than once. That's the issue. Then it is injective. So here I can see clearly that any horizontal line I draw will only hit the graph once at most. Okay, at most it will hit it once. So yes, it is injective. We then have surjective. Now, surjective has a horizontal line test as well, and that is that any horizontal line drawn will hit the graph at least once, so it's kind of the opposite. It's saying that you will always hit the graph when you draw a horizontal line. Here, we can see that that's not the case. I'm not going to use the horizontal line test for surjective because I find that it's confusing to have two horizontal line tests for two different things, and I think you need to be very clear about them. Instead, what I generally recommend is that you keep the horizontal line test for injective and use something else for surjective. So for surjective, really it's trying to understand, are all the possible y values used? So a quick way to do that is to compare the range to codomain. Now, because part A has asked us to work out the range, and because the question has so obviously given us that codomain as part of the function, I think this is a nice way to move, especially for this question. So our range we worked out was y is greater than 2. The codomain was defined in the original question as all the real numbers. So are all the real numbers the same as where y is bigger than 2? No, they're not. Because the range and the codomain are not equal, then it is not surjective. So it's not surjective. Now I have something that is injective but not surjective, and by that logic, no, it cannot be bijective. Question 3, another exponential function with, functions plural with points of intersection. This is a great chance for us to work with our exponentials in a slightly different way. So here we're given two functions, f of x, which is 2 over e to the power of x, and g of x, which is e to the power of x minus 1. Complete the table below, write your values correct to 2 decimal places where necessary. We are subbing in 0, 0.5, 1, and the natural log of 4. So you have your ln4 button there in your calculator. Log to base e. That's what natural log is, log to base e. So what you'll find is they kind of undo each other is probably the best way to think of it. So if you have e to the power of a natural log, your answer will just be whatever was in that natural log. So when we do that, we end up with something like this. Okay, your calculator will do all the work. You were asked to do this correct 2 decimal places where necessary. Part 2 then says in the grid on the right, use the table to draw the graphs f of x and g of x in the domain between 0 and the natural log of 4 and label each graph clearly. So this is what we end up working with. What you're going to have to do before you plot this is work out what the natural log of 4 is in terms of a decimal, so you have a better sense to plot. So this works out as 1.39-ish, okay? So that's where you're plotting. When we look at the graph, we can split this into 5 pieces below 1. So all of these represent a jump of 0.2. So 0.4, 0.6, 0.8, and so on. Okay, so that gives us a sense. It's a little bit crowded, so I just want to take this off before we do a bit of work on it. But that's how we will plot. So you have your 0, 2 is up here, and your 0, 0, and you just keep going. Do make sure that you label your graphs. They said that you need to label them clearly. You will lose marks if you don't. Part 2 then says use your graphs to estimate the values of x for which f of x equals g of x. So we're basically trying to find the point of intersection from the graph. So here I can see that it's there. Looking at what that actually means in terms of my number line on the x-axis, I have 0.2, 0.4, 0.6, 0.8. So it's somewhere between 0.6 and 0.8. So I'm going to say about 0.7. So it's about 0.7. Part B then wants us to solve this using algebra. So we're going to basically confirm what we've read from the graph. We're going to expect our answer to be roughly the same, so about 0.7. Let's see how this works. So our f of x is 2 over e to the power of x, and g of x is e to the power of x minus 1. To solve them, we're going to allow them to be equal. We literally follow what they've asked us. They've asked us to solve f of x equals g of x. Now, this is very complicated because we're dealing with e to the power of x's. You can work like this and that's absolutely fine, but I think the majority of students will struggle with it. And even if you do manage to do it, you'll probably be a lot slower at this than you would otherwise. So a more efficient way to work when we are more complex equations like this is to use substitution. So I'm going to let y equal e to the power of x. What that does is it simplifies it. It allows us to really see the question and we're able to work through it a little bit easier. So this becomes 2 over y equals y minus 1. Now I'm going to multiply both sides by y, the denominator, to get rid of my fraction. That becomes 2 equals y squared minus y. I now have a quadratic, so I bring everything to one side. So I'm going to bring that minus 2 over. I'm now going to solve it. So I'm going to factorize. I can use my shortcut for guide number. Minus 2 can be split into minus 2 by positive 1 to give me the negative 1 in the middle. So this is what I end up with. Y minus 2 times y plus 1 equals 0. That gives me two answers of y equals 2 and y equals minus 1. Now, I'm not finished because remember I used a substitution. So I need to go back and say, well, if y equals 2 and y is also e to the power of x, what does that tell us? So what that tells us is that actually e to the power of x equals 2. To solve this, I need to use logs. So you can use the little circle method. So I'll just draw in the circle method for anyone doing it that way. So that is log to base e of 2 equals x. Log to base e is natural log. You can use the little converter in your log tables, or you can think of it as taking the natural log of both sides. Whatever way you think of it, we should still end up with the same thing, and that is x is equal to log to base e of 2, which is the natural log of 2, whichever way you want to work with it. And they didn't tell us how to give the answer, but given our last answer was in decimal, I would be looking for a decimal answer here, and it works out as 0.693. So it's very close to our 0.7 that we had estimated from our graph. Let's look at the second answer. So the second answer was y equals minus 1. So e to the power of x equals minus 1. Now, straight away, I can look at this and say, actually, that's not going to work. You can try convert it, and then you'll find you get an error at the end. But I do think actually to save yourself some lines of work to really engage with, can I get an answer for this? Again, going back to what we talked about in an earlier question, e is a positive number. So there is no value of x that will give a negative answer. So it doesn't matter what power I put on a positive number, my answer will stay positive because I'm multiplying a positive number by itself so many times, and that really means multiplying positive by positive by positive and continuing to do so, which means we'll only ever get a positive answer. So it's not possible to have a negative answer for e to the power of x. But if you did continue with it, you did keep going, all you'd find is at the end you'd have an error. Question 4 looks at injective and inverse, and it is 15 marks. So show that f of x is equal to 3x minus 2, where x is an element of the real numbers, is an injective function. Now there's a few different ways that we can do this. I prefer to work in kind of a logical way. So f is a linear function with a slope of 3 and a y-intercept of minus 2. How I know that is I'm working with the idea of y equals mx plus c. It's so important that you can recognize that it's linear, so that has not no power, but really it's an x to the power of 1. When it's linear, we can use anything that we've done in coordinate geometry, and particularly that y equals mx plus c. That gives us some very quick information. I can then sketch this. So here's my x and y axis, and roughly this is what f of x will look like. I have my y-intercept here, which is at minus 2, and my slope, which is 3. Now, a linear function by its nature is injective since it's a one-to-one mapping. Okay, and that's fine, but I'm going to go even one step further. I'm going to say from the diagram on the left, we can see that it would pass the horizontal line test for injective functions. How we know this is if I draw a horizontal line anywhere, it will touch the graph at most once. Okay, so it means that the horizontal line drawn anywhere will touch the function, in this case our linear, our line, no more than once. And we can see this once crossing over, therefore is injective. Okay. Given that f of x equals 3x minus 2, find the formula for f to the power of minus 1, which is the inverse of f, so f inverse, and show your work. So f of x is 3x minus 2. To work with the inverse, the first thing we're going to do is replace that f, that notation of the name of the function, with the general y. So y equals 3x minus 2. We're now going to rearrange this formula so that we have it in terms. So in terms of y. We want x in terms of y. We want to isolate x. So I'm going to add a 2 to both sides. I want the x, and I like to have that on the left. So I'm going to flip the equation and then divide by the coefficient, which is 3. So I'm left with x equals y plus 2 over 3. Now you've done the bulk of the work. However, because it's an inverse function, we need to make sure that it is a function. And remember, functions, it's not any graph. There's some rules. We have the vertical line test to make sure it's a function. And we can repeat y values, but we can't repeat x values. So what we need to do is to change our notation slightly, and that is the x becomes the inverse function and we change y to x. So it begins to look like this. So it becomes, instead of x, the function, so it's f inverse of x, and then instead of y we put in x. Really important. This is a nice part 2 for the part 1 because actually we can use the fact that the function has an inverse to show that it is injective, because when we talk about inverse functions, so when we talk about working backwards, only bijective functions have an inverse. So only bijective functions have an inverse. So since this has an inverse, this function must be bijective. That means it is both injective and surjective, and that kind of proves our part I. So that's another way you could work. Question 5, completing the square, 25 marks. Part A, express the quadratic function x squared minus 10x plus 20 in the form x minus a squared plus k, where a and k are real numbers. So this is asking us to put this quadratic in completing the square form. And there's no coefficient, which makes this question a little bit easier. There is a video on quadratics to completing the square. I'll link the video below if you want to see some more challenging versions of this. So the first thing we're going to do is we're going to look at the first 2 terms, so the x squared and the x terms. And when we look at these two, we're going to create the bracket squared. So that creates x minus 5. So how we do that is the square root of the first, and here we have half the coefficient of the second. So think of your squaring shortcut. We're working backwards. Usually we double it. So now we're halving it. So it's the x is already used. So we have the minus 10, and that gives us minus 5. Now, this quadratic, or well, this bracket squared gives us a quadratic trinomial, but we've only used 2 pieces to create it. So let's take a look. When I expand it, I actually get x squared minus 10x plus 25. Now, the quadratic itself had a plus 20. We can work with this by taking away the 25 and adding 20, or in a case like this where it's quite easy to understand the numbers, you can say, well, this bracket gives me the 25. I wanted a 20, so to correct that, I'm going to take away 5. And that's our answer. So A is 5 and K is minus 5. So then it asks us to identify the minimum point of the function. So the minimum point is always given by the 2 numbers, one in the bracket and the one outside the bracket. So here, the minimum point will be AK. So here I get my x coordinate, here I get my y coordinate. The x coordinate, we have to be careful, the sign will change. Okay, the y coordinate, it doesn't. So from what we've done in part A, we have the 5 and minus 5. Part C then asks us to find the roots of the quadratic function, giving your answer in third form. Taking what we've worked out in part A, we're going to solve that. We're going to let that equal 0. We add 5 to both sides, and then we square root. We have to be very, very careful to put in our plus and minus before we put on the square root. This means there are 2 possible answers for when we square root. The final step is to add 5 to both sides. We put this 5 at the start rather than the end, so it looks more like our answer when we use the quadratic or minus b formula. So our final answer is x is 5 plus or minus root 5. That's our 2 possible answers. You can write them separate or leave them as is. Part D, what is the equation of the axis of symmetry for the graph of this function? So here's the function written in completing the square form. I'm going to sketch this out. Well, I'm going to take a picture of it, but really, like, this is not something super accurate we need to do. I just want to show you roughly what's happened. So here's our positive quadratic. Really the only thing that I've worked out, I know I've worked out the roots and I could put them in decimal, but what the completing the square form tells us is this minimum point here. So our minimum point is 5 minus 5. And the axis of symmetry, because all of our quadratic parabolas, the quadratic curves are symmetrical, we just want to put a line directly through that like this. Now, that is the axis of symmetry, and we want the equation of that axis of symmetry. This often causes problems because, one, it doesn't look like what we would maybe consider a traditional linear equation. And second, if you tried to work this out using coordinate geometry, it would kind of fail because the slope is undefined. It's a vertical line, so technically we cannot talk about that slope. We have no slope to work with. This is a special type of line that's called a constant. It's a constant because it doesn't matter what y value I take, the x value remains constant. So the actual equation looks like x equals 5. So what that means is it doesn't matter what y value I take, the x is 5. Now, like I said, this doesn't necessarily look like an equation, but this is an equation of a constant.